Let me discuss assignment 6, which is based on transportation problem with you. This assignment should have been discussed a little earlier, but anyway, so let us go through these problems. In the first problem, I want to show you how complementary slackness conditions can be used for the transportation problem. So, in the table below, balanced transportation problem is given to you, and as usual, the entries are the costs, and the right hand side and the row below is the demands, and the column on the right hand side is the supply. Now, I have given you a dual feasible solution u bar, which is equal to, disregard this infinity here, because you have, u bar corresponds to the rows. So, this is minus 7 8 3 0, and v bar is minus 4 minus 3 2 1 4. So, this is a dual feasible solution. You can verify it for yourself. And now, using complementary slackness conditions, you see you will only allow those xij's to be positive for which the Cij minus ui minus Vj is 0, because of the complementary slackness condition. So, if you can find an x bar which is feasible from among the cells for which the dual constraints are satisfied as equality, then you will have a primal dual feasible pair. And using complementary slackness conditions, again you can show that the pair x bar comma u bar comma v bar, which is a primal dual pair of feasible solutions, will also be optimal. So, this is what you have to do in problem 1. And if there are alternate optimal solutions, then also find them. That means, if for some non-basic cells your dual constraints are satisfied as equality, or the relative price is 0, then you can enter those cells into the basic feasible solution and get an alternate optimal solution. Right. So, this is problem 2. Now, problem 2, transportation problem given below, a feasible solution is indicated. Yes, and what is happening is that you see the number of supply points are 4, number of demand points are 6, so 10. So, you should have actually 9 basic cells. In any basic feasible solution, there should be 9 cells, but here we have 3, 3, 6, 9 and 12. So, this is a feasible solution, but not a basic feasible solution. So, I first want you to find out basic feasible solution from this given feasible solution, and you know that because the number of cells is more than 9, you will have quite a few theta loops, and so you have to get rid of the theta loops and then obtain a basic feasible solution. So, do that in this thing, and then check if the basic feasible solution obtained is optimal. Now, let us go to problem 3. Yeah, this is, here you see I am just trying to acquaint you with unbalanced transportation problems. So, I have given 2 of them here, and I want you to reduce them to balanced transportation problems, and we will discuss how. So, here for example, in the first problem, see the supplies add up to more than the demand points, the demands. Okay. So, therefore, what is happening is that your supply constraints will be satisfied as less than or equal to, because you will not be able to use all the supplies, since the demand is less than the total supply. So, therefore, your supply constraints will be written as inequalities. And in the second case, the second problem, you are given that the maximum amount available. So, that means again all the supplies need not be used up, and the demands are not exact. That means you minimum requirements are given. So, you may ship more than what is required. So, here actually you have inequalities for supply points or supply constraints as well as for demand constraints. So, both kinds of inequalities you have to handle here, and I will try to show you how to handle these 2 types of unbalanced transportation problems. So, let us see in the So, for the first problem, I am giving you a basic set, and I am asking you to constitutes an optimal solution when the supply at source 4 is 16. You see, if S4 is 16, then the sum of SIs is equal to sum of DJs. So, then it becomes a balanced transportation problem, and so you can immediately check whether the given set of cells, they constitute a basic feasible solution, and then verify that they also satisfy the optimality criteria. So, this is the optimal solution. Now, I am saying that we have to obtain optimum solution for the given problem, which is the unbalanced thing. So, okay. So just go ahead, starting with the given basic feasible solution, which is optimum for S4 equal to 16. You have to obtain an optimal solution now. So go ahead and do it. Fine. For problem 2, again I am giving you a basic set of cells, and I am saying that you can obtain a basic feasible solution xij bar for the given unbalanced transportation problem, reduce it to a balanced transportation problem by adding a sixth market, and the cost will be Ci n plus 1. In our case, n plus 1 is 6, and then your d6 is 2. So the difference between sigma Si and sigma dj, that is 2. So make that difference equal to 2, and so the demand d6 will be 2, right? And then I am telling you how to obtain the Ci n plus 1 here, right? And the formulae are given to you. So you have to take the minimum of, so this formula you can go through. So once you have these costs given to you, now with this cost you have a balanced transportation problem. The number of markets has gone up to 6, and then I am asking you to first obtain xij bar is an so actually these basic cells that I have given to you in the beginning, they constitute an optimal solution. So verify that it is an optimal solution. So once you have an optimum solution xij bar for the balanced transportation problem, then I am now asking giving you a formula for constructing a solution xij hat, and the formula is given here, the 3 formulae are given here, and now you can show that xij hat is optimum for the original unbalanced problem. That means you now verify the optimality criteria for the unbalanced transportation problem. So the optimality criteria does not change, even though the constraints are now not equality constraints, but less than or equal to kind. The optimality criteria will remain unchanged. So once I have given you this xij hat, just check that the given solution is optimum, okay, for the unbalanced transportation problem. So this is how I am trying to give you the treatment for unbalanced transportation problems. And in fact, it will be interesting to look up the literature, for example, K.G. Murthy's book only, and you will find many other variations of the unbalanced transportation problems. But since once you know your balanced transportation well, you can always reduce all these variations to a balanced transportation problem and get the optimum solution. Yeah. 4, I am just taken this again transportation paradox from K.G. Murthy's book. It's a modified version. I have modified the problem. So essentially what I am telling you is that S and D is one set of supply and demand, S hat and D hat is another set of supply and demand for a transportation problem, and S is greater than or equal to S hat and D is greater than D hat. This, since these are all vectors, that means component wise each Si is greater than Si hat and each Dj is greater than Dj hat, right. So now I am defining ZSD as the objective function value for the transportation problem. So the costs remain the same, right, with S as the supply vector and D as the demand vector. IfCij's are all non-negative, then one would expect, see this is what I am saying here. So one would, if allCij's are non-negative, then one would expect that since the volume of traffic for S comma D is more than S hat D hat, you would expect that the objective function value for S comma D, that means ZSD, will be greater than ZS hat D hat. But actually this is not what is happening. It is possible that even though you are transporting more goods or whatever it is, the traffic is more, your cost may still be smaller, right. And I am giving you an example here. So in this case, you see this is the table, and the 10 plus delta is the demand supply at source 2, and 25 plus delta is the demand at market 2. Then so now the solution shown in this tableau is feasible for delta between 0 and 2, and you can also verify that it is optimal for all values of delta between 0 and 2, right. But you see that the optimal cost is 1129 minus 19 delta. That means as delta increases, the cost will decrease. So this is the kind of paradox I am trying to show to you. And then now I am asking you further to work out the situation when delta is greater than 2, and you will see that for delta between 2 and 27, the cost continues to decrease as delta increases, okay, because in the optimal cost the coefficient of delta would be some negative number. So the cost will continue to decrease as the delta increases as long as delta is between 2 and 27. So, this is what we mean by a transportation paradox, but surely you can try to rationalize why this is happening. Okay. Now, problem 5, I want to make a point here, and this is, see, I have been saying that for a simplex algorithm, to combat degeneracy, which means cycling, you apply Bland's anti-cycling rules, and then you get the you can avoid stalling. That means you can avoid cycling, right. So, the same thing we will do for the transportation problem also. Now, Thapa and Danzig, I have given you the reference of the book. This has taken has given a transportation problem which cycles if you use the ordinary simplex algorithm, right. Now, and then I gave you an epsilon perturbation method also, which I feel, and for of course many other practitioners feel, is a faster one, faster than Bland's. So, now here I want you to apply Bland's anti-cycling rules to the transportation problem, for that problem which is given in Thapa and Danzig, and see the count the number of iterations and compare with the, because I have solved the problem with the epsilon perturbation. So, you should be able to compare. Of course, one problem is not enough to judge the performance of, but I just want to demonstrate to you that the Bland's anti-cycling rules become they make the algorithm slower for specially structured problems like transportation problems, because these problems have a special structure. So, the epsilon perturbation method is supposed to be faster. Okay. So, I hope you enjoy doing the assignment. So, let me get back to strongly feasible basis, and I thought I should have one or two more examples to make you more familiar, because we do not use them so often. So, here again I am trying to give you an show you, suppose this is a strongly feasible basis, a tree, because as you see, you can send a positive flow from every node to the root node. This is your root node, right. You can just check. Okay. See, here everything is this fine. So, now I will show you an iteration when suppose you the arc 8 9 is the entering arc. Okay, okay. I mean, sorry, what I want to say here is that here suppose the flow is 3 3, and I have to reduce the flow on. So, to reduce flow on arc 8 9. So, that means the orientation of the cycle is going to be this, right. This is the orientation of the cycle, because I have to reduce the flow. And you can see that, for example, here the flow can get reduced by, so this will be by 1 unit, right. Here the flow can go up by 2 units, then here again the flow can decrease by 1 unit. The orientation is like this. Here the flow can increase by 1 unit, by 1 unit, and by 1 unit, right. So, essentially your delta comes out to be 1. So, let me, or if you want to write, what I mean is that you are going this way. So, here is minus delta, then this will be also minus delta, this will be plus delta, and so on, you can write down. So, now let us see what are the blocking arcs here. The blocking arc, this is a blocking arc, right. Then this is a blocking arc, and these are all blocking arcs 3 5 5 7 7 9, because all of these limit the increase of the flow by more than decrease of flow by more than delta, by more than 1, right. Is it okay? So, and this is the orientation. So, how do you decide the exiting arc? Exiting arc, what is the exiting arc here? So, remember we said that we will start, and this is your apex node, right, because you have these two nodes, you take the path and then they meet both path towards the root node. So, they meet at 3, this is your apex node. So, from no apex, this you start along the orientation of the cycle, because the orientation is like this. So, you start from here and then you go on, all these are blocking arcs, you come up here, then here, this is the last blocking arc. For us, this will be the last blocking arc, right. So, that means I will exit this one, and you see then the tree will hang by like this, and in that case you see if this goes up by this becomes 5 6. So, you will still be able to flow more than, because see now what will happen here, the flow will be 0, but when you exit this, these arcs will be hanging like this, and the direction of this arc will become towards the root. Remember, for all 0 flow arcs must be pointing towards the root node. This is the rule, right? And so this will again, so exiting arc will be the last blocking arc, right, which is in our case 3 4, right. And the remaining tree, the new tree, when once I update the flow, would be again a strongly feasible tree, right. Then we had also mentioned the case that how do you get a starting feasible solution, which is a strongly feasible tree, right. And I had mentioned that when you use phase 1 and you get the artificial arcs as your part of your feasible tree, starting tree, then that will be a strongly feasible tree, because artificial arcs do not have any, so no upper bounds, no upper bounds on artificial arcs, right, no upper bounds on artificial arcs, right. So, therefore, you see that if this, so this will be my root node in this case, this is the root node. So, then you see there is 2 units of flow. So, I can decrease the flow on these arcs, all on these arcs I can decrease the flow, and on all these arcs I can increase the flow. Sorry, say it again. See, from here I should be able to, oh, is this, so for these arcs you can increase the flow, and we had said that the okay, right, because there is no upper bound. So, I can increase the flow here, right, on arc 1 6 and 3 6 I can increase the flow. So, there is nothing like a saturated arc, and there is nothing like a 0 arc in this case when you have, so therefore, both the conditions do not apply. I mean, in the sense that by default the conditions apply, right, because there is no 0 arc here and there will be no saturated arc, since there are no upper bound constraints. So, a starting phase 1 starting tree will be a strongly feasible tree. So, you can begin your iterations by that. And so, it has been effectively shown that using strongly feasible basis will avoid cycling. But again, stalling is a new is a different problem, and there are methods to tackle stalling also. Okay, so that should take care of your min cost flow problem. Then we come back to the shortest path problem, and I had shown you. So, the shortest path problem yes, and I had shown you that this is a special case of the min cost flow problem, where you are only having one unit available at the point from which you want the shortest path to be found, and up to the point node T. So, S and T, we said we want to find a shortest ST path, then there is one unit available at node S and one unit is demanded at node T, and you are computing, and theCij's are the distances or the cost of traversing the arc ij. So, that is there, right. So, and I showed you that you can solve it by the primal dual algorithm by repeated applications, right. Okay, and that turned out to be building up the path from T backwards, right. So, now if you just look at what was happening in the primal dual algorithm from the starting node, that becomes and of course, what one can say is that you are not actually applying the primal dual algorithm, but it is the primal dual algorithm in a sense, but your computations become very simple. So, let me first give you the algorithm, and then we will discuss this thing. So, this is known as Dijkstra's algorithm. This whenCij's are greater than or equal to 0. So, this is a special case. That means, the Dijkstra's algorithm will not be valid if someCij's are negative, and then later on we will discuss the case when theCij's can be negative. So, we will have another algorithm for computing the shortest path between any pair of nodes. So, Dijkstra's algorithm says that you define a set W as node X such that the label rho X denotes the LENGTH length of the shortest path from S to X using nodes in W only. Okay. So, let me define a set W as the set in which I keep adding those nodes for which I have shortest length of the shortest path from S to that node using only the nodes in W, and that label I will give it rho X, right. So, that means I will constantly go on building my set W, and the moment T belongs to W, I have found the shortest path from S to T, right. So, now how do I do it? So, to begin with S belongs to W and rho S is 0, okay, because that is a starting node, right. Then and let to begin with you have this, and let me say then here, and rho X is equal to C S X if S X belongs to your arc set, right. Now, here right in the beginning I had told you that we will be doing it for a directed arc, and so this is always understood that V is your node set and A is the arc set. So, I will not write it every time. So, we say that this is C S X if S X belongs to A and is equal to infinity otherwise. So, in the beginning, when for all nodes which are connected to S by an arc, I will give the label as the actual cost or the distance of the arc S x, and for all other nodes it is infinity for the arcs which are not there, right. So, we have this. Then what we do is we say that select X such that rho X is minimum rho y, minimum of rho y, y not belonging to W, right. So, you have given the labels, that means all the labels are defined here in the beginning. Then I will pick up that node for which the label is the smallest for all nodes which are outside W, right. So, initially only S belongs to W, then you have labeled all the nodes, and then you look for the one which is the smallest label, and you select that node, and then you say that your W goes to W union X, right. And so, you continue and then you update. So, update the labels rho y as minimum the old label and rho x plus C x y. See, that means you have pictorially. So, you update the labels as the for every for y. Okay, this is for all x belonging to W, right. Update the labels for y not belonging to W, right. Then you do it this way, right, and continue with the algorithm. Right, that is, go back to, I should have written here, maybe if you want me to write this is step 1, then this is step 2, and this is step 3. So, continue, that is go back to step 1. Okay. So, I have to now validate the algorithm, and that means what I have to say is that what you end up with would be your shortest path to the node T. So, what are we saying here is that the moment when you select a node this with this criteria, then the label, because now W becomes part, X becomes part of W, and by our definition rho X must represent the length of the shortest path from S to X, right. Okay. So, why do I say that? So, pictorially what was happening is that, see, I have this set W here, then I have a node X here, and I say that this is the minimum one, because you have so many other nodes outside W. So, I choose the one which has the smallest label, and then I am saying that this has, that means right now rho X represents what? Rho X would represent, well, I will add X to W, that means rho X will represent shortest. So, S is here, right. It will be the length of the shortest path from S to X by using nodes of W only, right. Okay. Now, what can, I mean, suppose that, let us say, suppose it is not true. That means, suppose there is another path from S to, so suppose this is P. So, suppose there is another path to X from S going through a node P which is outside W, right. Then what will happen? Yes, see this path, that means your, I am saying that rho X represents this length, which is the last node is somewhere here, and then, so therefore, what we are saying is that rho P plus C P X is less than or equal to rho X. Yes, because rho X I am saying is the label for X right now, and rho P is the label for P, and the shortest path to X is via P. So, that means this is the, so this is rho P plus C P X. Yes, but C P X is greater than or equal to 0, which implies what? That rho P must be less than or equal to rho X, or in fact, I will say that this is less than rho X, which is a contradiction of the fact that rho X was the minimum one. So, this is not possible, right, and therefore, the, yeah, but C P X implies this, right, this contradicts. That the fact, so the fact that, yes, I will have to, so this contradicts the fact that X had the smallest label. I think I am writing the spelling of label. Okay, we will verify. Okay, fine. Yeah. So, therefore, X must be, rho X must represent the shortest distance from S to X by using nodes of T, right? And therefore, once T belongs to W, we have the labels representing shortest paths, shortest path lengths representing. So, we have the labels representing shortest path lengths from S to each of the other nodes. Okay. Because now in the process of computing the shortest path from S to T, you have managed to compute shortest paths from S to every other node, right. And if you just start your dual simplex algorithm, like if you can reverse the network and have T as your starting node, then you will see that the every iteration of Dijkstra's algorithm matches with your primal dual algorithm. So therefore, this is nothing different, but the thing is that without the justification of the primal dual and going through that whole process, you simply do this, and the argument, simple argument, that you, by defining W this way, you can say that the labels that you are computing are the shortest path lengths. So it's a shortcut, real, because we are exploiting the structure of the network, and we are using the fact thatCijs are non-negative, right? So let me give you an example here. So if this is the network, the distances on the arcs represent yourCijs, and you want to find out the shortest path from 1 to 6. So we will start with the, so I can just start writing the labels here, right? So initial labels would be, you see, as I said, 0, and then for arcs, for nodes 2 and 3, the labels would be 3 and 5, and for all, so it will be 3, 5, and infinity. So this will be 1, 2, 3, 4, 5, and 6. So 6 labels, and these are the things, right? The starting labels. Right? So then my initial W consisted of just node 1 with label 0, right? So now you see that, so I'll just indicate by star the ones which, and see the name for the nodes which get admitted to the set W are called permanently labeled, because then their shortest path length or the label will not change. Remember, we only update the labels for Y not in W. So the nodes which are already in W, the labels do not change. Okay, so this is it. So now I'll choose this one, right? So I should have put the star later on, right? So since row 2 is the smallest, is the minimum one, right? Therefore, your W now includes this, right? And then we have to update. So that means you have to look at all nodes which are now connected to both 1 and 2, right? See, the minima was over all nodes in W, right? You're trying to find out. So we can just do it right on the network here. Say, for example, for this one, this is connected to 4 is connected to 2, and the label here would become 8, and the original old label was infinity, right? So that means here I can write down 0, 3, and this one would become 8, right? Then for node 3, for example, the earlier node was 5, and the label was 5. From 2 you can come to 3, and the distance is 3 plus 1, 4, and I don't have to do the minima, because I know that the others are allCijs positive. So I cannot, for example, in fact I cannot come back to 3 from 2 by any other route. So this is the only possible one. So therefore 3 plus 1, 4. So this one also gets updated to 4, right? And then 2, 5. 2, 5 you have 3 plus 1, right? And you have 3 plus 1 plus 4. So 8 and 3 plus 1, 4. So the minimum is 4, and that is smaller than infinity. So this is this, and this is infinity. So these are your new labels. Originally you had these permanently labeled. Now you choose the minimum one. So you have in fact 2 of them at the same time. So I will choose both of them. Nobody stops me from not labeling more than one, right? So therefore my W then, in case, that becomes 1, 2, 3, and 5. Okay. So therefore now you have this labeled permanently, this of course is labeled permanently, this is labeled permanently, and this is. So, now on the graph you can see immediately. So, to update, what will I do? From here you can look at this one, yeah, from 3 you can reach 4. So, this is 5 plus 2 7, and the earlier one is 8, right, and there is no other path to reach 4. From 2 there is no other path, right. So, 7. So, that gets updated to 7, and from 5 you see that this will get updated to. So, 3 plus 4 is the old one. So, 4 plus 3 7. So, now you have the new labels are 3 4 7 7 sorry 4 and 7. So, both of them get permanently labeled, right, and so your W is now 1 2 3 4 5 and 6. So, just 3 iterations, and you could label the find out the shortest path. I chose a very simple example. There can be many more routes to choose from, but anyway, still you see at each iteration you must. So, what is happening is, and now let me just introduce an element of concept of complexity of an algorithm, which I have not so far talked about. But you see here what is happening. Your size of W will induct at least one node, see, at least one node in each iteration, right. And so, therefore, a number of iterations is n at most, right, order n in fact, because as we saw in this case it only 3 iterations, because I could label 2 nodes at a time. So, it will be order n, right. And then at each iteration, how much work are you doing? At each iteration you are just updating the label of the ones which are not in W. So, again this is order n, because you are simply adding and comparing the minima. So, which is because we say that all these elementary operations we consider them as one unit of work. So, therefore, number of iterations this, and work done at each iteration is order n. Yeah. Therefore, you say total complexity, that means the number of, it is not very coming out very nicely, total complexity is order n square, which is really nice, because at most in order n square steps, calculations of addition, comparison and so on, you will be able to find out the shortest path from in a network with having n nodes. So, let me now consider another shortest path algorithm where the Cij are allowed to be negative, because Dijkstra's algorithm we saw that the proof, the validity was dependent on the fact that theCijs were non-negative, right. So, Floyd-Forshall algorithm in fact finds the shortest paths, between all pairs of, not just n one pair, all pairs of nodes whenCijs can be less than 0, right. So, but then again when you have negativeCijs, it is possible that you may have negative cycles in the network, right. So, part of the cycle may be yeah, I can. So, once if there is a negative cycle present in the network, then the shortest path length has no meaning, because I can go on traversing the negative cycle as many number of times as I want, and I can go on reducing the shortest path length. In fact, so the shortest path lengths would not be bounded. I can make them go up to minus infinity. So, that is the danger, and so any algorithm which claims to compute shortest path lengths when theCijs are negative should also be able to detect the presence of negative cycle and then stop, because once the negative cycles are present, then the shortest path lengths have no meaning, because you cannot define them, right. So, all Cij can be negative. It also detects negative cycles when present in the network. And the idea is simple, and I will then give you later on its validity. So, it detects negative cycles when present in the network, right. So, definition is simple. What I do is we define the quantities Uij m as the length of the shortest path between node I and node j that uses the nodes 1, 2 to m minus 1 only. Okay. The idea is that again it is a partial shortest path that I am computing, and the same that we did in Dijkstra's algorithm also, we limited the shortest path to the nodes of W. That is, I can only use the nodes of W and then go on building the shortest path. So, here also we say that Uij_m will denote the length of the shortest path between node I and node j when only nodes up to 1 to m minus 1 have been used. It is not necessary that all of them get used, but what we are essentially saying is that nodes m to n should not be used in the construction of this shortest path from I to j. This is what we do, right. So, and therefore, Uij n plus 1 will denote the shortest path length, because by that time I would have used all the nodes 1 to n, and therefore, my claim should be, we will prove this, will denote the shortest path length. Yeah, I will keep using. Okay. So, once I have gone through all the nodes, that means there will be n iterations to this algorithm again, and so we will then be able to claim, and I will prove to you that the Uij n plus 1 will denote your shortest paths. So, then how do I update? So, the idea here is that you write Uij m plus 1 as the minimum of, that means when you go from m to m, if you want to include the node m in the computation of the shortest paths, then you will say that this is Uij_m or Uim_m plus Umj_m. Okay. So, this is clear. If the shortest path from I to j, when we are allowing the inclusion of the node mth node, so either it goes through the node m or it does not. If it does not go through the node m, then the earlier shortest path remains intact. So, this must denote the length of the shortest path, because it is not using the node m. If the node m is used, then obviously it should be made up of the shortest path length from I to m, right, because this one does not include the node m, right, up to m minus 1. So, you are including node m here. So, this plus Umj_m. So, from I to m, m to j. So, this is the only two possible things, and therefore, if you choose the minimum of the two as Uij_m plus 1, then you have updated the Uij values, and you are saying that this will be the shortest path when you allow nodes up to 1 to m to be included in the shortest path, right. So, this is the thing, and so once you say that this is this, you can say that Uij n plus 1 actually you can now write as Uij, right, and you see that this will, because of this will always satisfy uik plus ukj. That means, if you take the triplet ikj, because you are choosing your updating your distances shortest path length by this formula, once you have done it for all the nodes, then of course there will be no, because these things get fixed up, and so uij will be less than or equal to uik plus uk is a sufficient condition for, right. So, this is your sufficient condition for, so this is sufficient condition for optimality. That means, the set of numbers uij indicate satisfy all these, that how many will be there, and yes. So, let us see, we said that we will have n iterations for each pair, because you are computing from 1 to n plus 1 n iterations, and then you are doing, or maybe after I show you the computations you can have a better feeling, and you are doing it for n square pairs. So, your computation should not be more than order n cube, right. I mean, so the if you just in a very rough way count the basic number of computations that you have to do, that will not be more than order n square. Now, we have a very nice way of representing the computations for these quantities through the matrix, and so here let us write out, suppose you are given this network, okay. Again the numbers are theCij's. So, you can see that quite a fewCij's are negative, and so let us show the calculations for the Floyd-Warshall algorithm on this the matrix. So, I have this, so the numbers, node numbers are here, and then so UIIs will always take to be 0 right now, right. The starting thing, you can say that the CIIs C11, C22, C33, C44, C55 are all zeros, and this gives you 1 to 2, 1 to 3. So, these are the shows you the distance arcs, distance matrix, right. So, then you want to compute, for example, uij. So, this one is uij1. So, I am calling the matrix capital U1, and the components are uij1, right. So, this is uij1. Okay. So, let us use the matrix representation, and I will try to show you the recursions for the Floyd-Warshall algorithm. So, for example, if you want to compute u212, let us say u212, right, then this will be according to the formula minimum of u121, and then it will be u111 plus u121. So, you see here, and so the thing to remember is that these two indices must match, right. So, u11 and this is 0. So, this is u12. So, there is no difference. So, in fact, I want to show you that when you are doing the computations for u2, that means you are including the node 1. So, the interpretation for this is that you want the shortest path between 1 and 2, where node 1 is included. So, either you include the node 1 or you do not, fine. So, this would be the computation, but you see it will not make a difference, since we are taking the diagonal elements to be 0. So, this is this, right, and here the trick is, so okay, for all distances here for the corresponding nodes, and for this, for the pair of nodes and this, there will be no change. Okay. It is only for the other these things that the change can take place, and then I want to show you, say for example, consider 2 3. So, 2 3 would be yes, here u2 1 would be minimum of u2 sorry, this is 2 3 1, and then it will be u211 plus u131, right. And let us quickly see that. So, you are wanting the distance between 2 and 3, and so if you include the node 1, then it is 2 1 and 1 3. So, this is 2 minus 1, which is 1, and so there is a change 1 3 u2, this is 1. Okay, sorry. This is u2. So, 2 3 is 1, right. Initially it was 2. So, the moment this change takes place, then I will record the last node visited, that means the change came because of node 1. So, then you can immediately trace the path, because the path from 2 to 3 has to go via 1. So, therefore, your shortest path right now when you are allowing to add node 1 is 2 1 3. Okay, that is the path. So, this matrix will record the changes that occur and the last node that you visited while finding out the shortest path. Okay. So, this is it. So, now then you can check that no other change takes place, and this is it, right. And so, similarly you will compute, this will be your u 3, okay, and then this will be u 4. Okay. And now, here we just want to, so for example, when you want to compute u 3, then we will underline the this thing here, second row and second column. Okay. And in this one, so now again there will be no change for the pair of nodes in this row and in this column, but there will be, you can consider, for example, now I can just maybe show you that this has changed, because there is a recorded node here. So, that is 1 4. So, 1 4. So, the idea is that you look at this and then you just go up to the row which you are considering. For example, we are allowing to include nodes 1 and 2 in the shortest path, right. So, this will be this and this will be this. So, you will compare this entry. I am looking at this recursion formula for you. So, this will be this entry and compare it with the sum of these two. So, 1 minus 1 is 0. So, obviously, 0 is smaller than infinity. So, that changes, and so 1 4 the distance becomes 0, and you visited, and that came through the node 2, right. So, when you want to trace the path from 1 to 4, say for example, then it tells you to go to 2. So, from 1 to 2 and 2 to 4, because there is no change here for 1 4. So, the path you immediately have 1 to 4, and the length of the path, the shortest path when you allow nodes 1 and 2 to be included in the path is 0. Okay. So, this is the idea. So, when you are computing u 4, then you will circle the third column and the third row, and again make the same computation, right. Any entry you take here, then you all you have to do is to go this way and this way, then compare this with the sum of these two, and whenever you find a smaller number, you record that. So, for example, you can just verify that these are the 3 entries where the change took place, and then when you allowed nodes up to 3, then you will have this computation. You can please check all my computations here, there might be some error, but anyway the change takes place because of node 3, and you see this is what we want to point out, that u 4 4 u 4 4 is negative. That means the there is a negative cycle, and you can immediately check the cycle, because this is 4 to 4. So, to do that, the change came place from node 3, right. So, that means you go to 4 3 4 3, and then you are supposed to, then 4 3 you can look at the this one here. Okay, there is no change 4 3. So, your path should be 4 3, and then at 3 the change took place, yes, here the change took place via 2. So, 3 2. So, you have to visit 2 and then you go to 4. So, if you look at 4 3 3 2 2 1, yes, 4 3 is minus 1, 3 2 is 1, 2 4 is this. So, therefore, the total length of the path is minus 1, and hence there is a negative cycle, and so we stop here, because now the problem is in a sense infeasible, because the shortest path length is not defined, since I can go on reducing the shortest path length by traversing this cycle again and again. So, you can see everything right on the graph, and through this matrix method you can compute these distances, and the complexity is order n cube. It also tells you the presence of negative cycles if there are any, and you can stop.